I don't want answers. I want rules. Okay, so that we can kind of generalize some things and figure out where we're going to go with this. But it says on a multiple choice test with 4 possible answers for each question, what is the probability of answering a question correctly if you make a random guess? Which rule would you use for this? I'll give you some choices. What's that? Okay, equally likely, which the rule, I guess we would call it more classic probability, right? We would use our classic probability formula. We can always come back to the classic formula for probability, which is going to look at, okay, the probability of getting it correct is what? The number of, well, on the bottom, total number of outcomes. And up top, what? We have to have what kind of outcomes? Well, that's the bottom. But up top, if we're interested in the probability of being correct, it's 1. It's the number of correct answers. Okay? What's that? We would assume because the person is guessing. It's called classic probability. Classic probability. Yes, that should be on your flow chart somewhere. Okay, so probability of getting it correct is the number of correct answers over the total number of outcomes, which I believe is going to be 1/4. Okay, but we got to think about the rules, all right, that are available to us. Okay, so questions about that? Yes. Well, whatever choices are available, you'll pick from the choices that are there. Okay. All right. It is still multiple choice mostly. Okay. All right. Here's another problem. A bag contains 2 red marbles, 3 blue marbles, 7 green marbles. If a marble is randomly selected from the bag, what is the probability that it is blue? Okay, so again, we're going to use what? Our classical formula for probability. So probability of blue equals what? How do we describe it? Number of blue marbles. Total number of marbles. Okay. As you continue to study, it's really important that you think about it first generally so that you can use that not just on the problem, but lots of different problems. Okay. So the number of blue marbles is 3, and the total number of marbles is 12. And so 3/12 reduces to 1/4. Okay. All right. Questions about either of those? Okay, good. All right, number 3. In a poll, respondents were asked whether they've ever been in a car accident. 138 respondents indicated that they've been in an accident. 494 said that they had not been in an accident. Of these respondents, or if one of these is randomly selected, what is the probability of getting someone who's been in a car accident round to the nearest 1,000th? Okay, so again, probability of accident, that's what we're looking for, right? Okay. Equals what? Or the number of people who've been in an accident, right? Okay. And we're going to divide that by what? Total number of people. Okay, this one really is what kind of probability? Not classical. Relative frequency. Formulas are essentially the same, but the source is different. Okay, these numbers come from observations or poll or something like that. Well, it says a poll. Okay, so the number of people was 138. Very good. And the total is what? 632. This time we had to add together to get our total. So divide 138 by 632. That will give you the answer. Okay, questions about that? Okay, good. All right, what about number 4? Find the indicated probability. Refer to the table, which summarizes the results of testing for a certain disease. Okay, so there's the table. If one of the results is randomly selected, what is the probability that it is a false negative? Test indicates that the person does not have the disease when in fact they do. What does this probability suggest about the accuracy of the test? Okay, so how would we figure this out? What rule are we using? Okay, relative frequency, classical. Those are pretty much the same, just different sources. So number of what? False negatives. And we're going to divide that by the total. Very good. Okay. So subject does the test results that the person doesn't have the disease when in actuality they do. So we've got 4 false negatives. Does everybody agree? Okay. 4, and then our total is, what is it? 309? 309? You sure? Okay. Okay, 4 over 309. So that comes up to one of our decimal values. What value does it come up to? C. Okay, 0.0129. The probability of this error is low, so the test is fairly accurate. Fairly accurate. Questions about that? Okay. Let's say, that's a good question. When would the total be, when would we restrict the total if we had given? If this asks us for the probability of disease given, let's say, what were false negative or negative result. Okay, then in that case, I would ignore all positive test results because we're given that the person got a negative result, and then the total now becomes 176. That's my bottom number. That's the total of negative results, and then we were interested in those that actually had the disease, so it's 4 over 176. Very good question. Okay, probability of disease given negative result will be 4 over 176. Oh, thank you. Okay. All right. Number 5 is one about the complement. It says find probability of A given that probability of A equals 0.732. It looks like a typo. Ideally, I mean, the answer would be what? 0.732. But what if it was probability of A complement? How do we find that? Okay, probability of A complement equals 1 minus the probability of A, 0.732, which gives us what? Is it 7 or 6? I don't know. .268 is a choice, yeah. 0.268. Okay, questions about that? All right. All right, very good. Okay, number 6. Based on meteorological records, the probability that it will snow in a certain town on January 1st is 0.185. Find the probability that in a given year it will not snow on January 1st in that town. What rule are we using here? Complements, right? It's either going to snow or not snow on January 1. Okay, those events are complements. So the probability that it will not snow equals 1 minus the probability of snow. Probability of snow is 0.185. And so we get, I think, 0.8185. C. Any questions about that? All right, number 7. A sample of 100 wood and 100 graphite tennis rackets are taken from the warehouse. If 6 wood and 14 graphite are defective and 1 racket is randomly selected from the sample, find the probability that the racket is wood or defective. Okay, what do you think we need to do here? What is it? Addition rule? Okay, certainly going to use the addition rule because we're talking about or. Okay, what else might we need to use here? Could a racket be both wood and defective? Yes, so they are not mutually exclusive. Okay, we're talking about probability of wood or defective. Okay, you asked the right question. We said or is addition rule. We asked whether or not the events are mutually exclusive. We said no, they're not, because a single racket could be wood and defective. So the addition rule for events that are not mutually exclusive is the probability of wood plus the probability of defective minus the probability of both. Okay? But something else we're going to need to use that we don't have yet. Well, maybe we have it. I don't know. Maybe we do have it. All right, can we put the numbers in? What's the probability of wood? 0.06? Just wood, period. Whether it's defective or not. It would be 100, okay? They're 100 over how many? Sounds like there's 200 altogether, right? What we're missing that I think I might have done is a contingency table. Remember we talked about setting up the contingency table? That might be helpful. This is an example of a contingency table. And so sometimes we're given a problem like this, we need to come up with our own contingency table. Okay, I'll put it over here. We've got 2 categories. We've got wood and graphite, and we also have what? It works or it's defective. Okay? So a sample of 100 wood, that's how many of those we have all together, and also 100 graphite. Okay? We've got 6 wood that are defective, which means how many of them work? 94. Okay? Then we've got 14 graphite that are defective, so we've got 86 of those. Okay, now that we've got that summarized, you know, it's easy for us to see we've got 100 wood. We've got over a total of 200. We've got how many defective? Altogether, 20. All right, 20 over 200. And then how many are both wood and defective? 6 over 200. Okay, so I get 114 over 200. Questions about that? Okay, very good. All right, we've got another table. Okay, the table below describes the smoking habits of a group of asthma sufferers. If one of the 1,197 people is randomly selected, find the probability of getting a regular or heavy smoker. Okay, so which rule are we going to use? Addition rule. Okay, because we've got keyword or, so probability of regular or heavy. Okay, and are these events dependent? I'm sorry, are these events mutually exclusive? No? Okay, look at the table. Does it look like we can have people who are regular smokers and heavy smokers simultaneously? No, they've divided those out into two non-overlapping categories. Okay? So in this case, they're mutually exclusive. Person's not going to be categorized as a regular smoker and a heavy smoker. So we would just say the probability of regular plus the probability of heavy. Okay? Probability of regular is what? Okay, we go back to our formula for classic probability. So we're going to look at the number of regular smokers, okay, which is 162. We're going to divide that by the total number of smokers, which is, okay, very good, 1,197. Same thing for heavy smoker. Okay, we get the total number of heavy smokers, 78 over 1,197. Okay, add those together. That should give you the answer. Okay, questions about that? All right, very good. All right, I think we hit contingency tables and addition rule pretty well in that test. I don't know if you'll see that much of that in the actual test. But anyway, next question. Find the probability of correctly answering the first 5 questions on a multiple choice test if random guesses are made and each question has 6 possible answers. Okay? All right, so that says a lot. I would focus first, though, on what the problem is asking me to find. Probability of what? Okay. Probability of correctly answering the first 5. So, answering 5 correctly. Okay, so a couple of ways I can approach this problem. I could try to use some of my probability rules, or I could possibly use some of my counting rules. Okay, it just depends on how you think about it. But let's go the probability route first. So I'm answering all 5 correctly. Which keyword is that going to be? And, right? We're going to get correct, and correct, and correct, and correct, and correct. Okay, and there are 5 questions. The person making a guess, each question has 6 choices. So what's the probability that they get it right? 1 over 6, right? So, all right, we already said and. Know the probability of getting a single question answered correctly. Are the questions dependent or independent? They're independent since they're guessing, right? If I'm guessing, it's just like tossing a coin, you know. Exactly. What they get on the first one doesn't really affect the probability of the next. Each one, they're randomly guessing. So I could write out some details about this. It's probability of correct, and correct, and correct, and correct, and correct, and correct. All right, so we're using multiplication. We ask, are the events dependent or independent? We decided that they were independent because the outcome of the first doesn't affect the probability of the second. So that's going to be probability of correct to the 6th power. And then, not the 6th, but I got too many choices, 5th power. And then the probability of answering it correctly is 1/6. So we get 1/6 to the 5th power. Okay, which comes up to what? B? Okay, very good. All right, so we used our multiplication rule to get that. All right. Counting rule, if I wanted to, could have done the same thing. I would have asked myself, how many different ways can a person answer the questions on this test? There are 5 questions that we're looking at, 6 choices each. So fundamental counting rule would tell us to multiply 6 times 6 times 6 times 6. I think I said it enough times. Which would, I'm guessing, come up to, I don't know, whatever the number is. I'm guessing it must come up to 7,776. Is that what you got? Yeah. Okay. All right, did you use the little house top right above the division key? 6 raised to the 5. All right. Then we ask, well, okay, fine. If there are 7,776 ways to fill this form out, these 5 questions, how many of those result in all 5 of them being answered correctly? How many ways could all 5 of them be correct? 1, right? There's only one. Well, no, it's not that there's one correct answer. There's only one correct answer key. Does that make a little more sense? Let's say the key is A. It doesn't matter. Let's say that's the answer key. All right, so even though we might be able to, the students could answer it in these 7,000 different ways, there's only one way where all of them would be correct. If this is the key, then it has to match this. There's only one way. Now, if we could make this question harder and start talking about, well, how many ways could you get maybe only one right? Okay, how would we answer that? Well, no, if we said only one, how many ways could you answer this test and get only one question right? That's what I'm thinking, but it might be more than that. Yeah, but what about all the different wrong choices? Yeah. Okay, so let's not talk about that. But when it comes to answering all of them right, there's only one way to do that. If this is the answer key and you're going to get all of them right, these have to be your answers. Does that make sense? Think about a test. Think about this test. All right, how many ways the test you're about to take? How many ways can you answer the test and get all the questions right? Only one. Same thing here. If we're interested in knowing how many ways they can answer and get all of them right, there's only one way to do that. Now, if we start, saying, well, maybe you get this one right, but not this one, that starts to change things. But there's only one way to answer the test and get them all right. So it's 1 over all the different ways, which gives us the same answer that we got. No, you could do the fraction on your calculator if you wanted to. Did you go to math fraction after that?
It just says error.
Okay, it won't go back to it? Yeah, so I would do 1 over, oops, that's not a 1, 1 over 6. I'm going to raise that to the 5th. All right, it's in scientific notation. Let's see what happens if it'll give it to me.
Why would mine do that?
I don't know.
See?
Okay, yours didn't do it. Okay. Well, then in that case, if you feel confident about the answer, then like you said, go back and just kind of compare it to the choices that are there. Okay. All right, very good. Okay, next problem. A batch consists of 12 defective coils and 88 good ones. Find the probability of getting 2 good coils when 2 coils are randomly selected if the first selection is replaced before the second is made. Okay, which rule? Well, first, even if you don't want to answer that question, what are we looking for? Probability of 2 good coils. Very good. Okay, and if we had to restate that using our keyword words, we would say what? Good and good. Which indicates for us which rule? Multiplication. All right. And so we're going to ask ourselves, are these events dependent or independent? Independent because of what? We're putting one of the first coil back before we select the second one. So it's the probability of good times the probability of good, or we could just say the probability of good squared. They're independent because we replaced that coil before we took out the second one. Okay, what's the probability of getting a good coil? Goes back, almost all of our problems will go back to the classic formula of probability at some point. So the probability of a good coil is going to be what? 88 over 100. Okay, or 0.88, and then we're going to square that. Okay, whatever that comes up to be. All right, what'd you get? D? Okay, 0.7744. Okay, questions about that? Okay, good. All right, another problem. An IRS auditor randomly selects 3 tax returns from 45 returns, of which 15 contain errors. What is the probability that she selects none of those containing errors? I'm going to pause right here and let you think about this one on your own. Okay, what's your thinking? Okay, thinking multiplication rule. Okay, Because we're interested, what is the probability that she selects none? Okay, so probability 3 with no errors. Okay, so no errors, no errors, and no errors. Okay, and says multiplication rule. We're going to ask ourselves, are these events what? Dependent or independent? Okay, and we say dependent because what? All right, she's selecting 3. We have no indication that they're replaced. All right, so if it's selection without replacement, that makes the events dependent. So this is going to equal the probability that the first is no error. I'm going to call that NE. How about that? Okay, times the probability that the second is no error, given that the first was no error. This is what we call conditional probability, times probability that the third is no error, given that the first and second were no error. Okay, so the probability that the first one is no error is what? Okay. All right, let's see, altogether it's 45 returns. 15 contain errors, which means 30 of the 45 don't, right? First is no error. So it's 30 without errors, am I right? So it'd be 2/3, right? Okay. All right, but we took that one out. All right. So what's the probability that the second one is no error, given that we've removed one that was no error? 29 over 44. Okay, times the probability that the third is no error. It's a good one. Okay, 28 over 43. Okay, and on your calculator, you can just multiply the numerators and divide that by the product of the denominators. So I've got 30 times 29 times 28 divided by, it's going to be really important that we put the denominator in parentheses if we're doing this in one step. I got 0.2861. Okay, questions about that? All right, very good. Okay. Did you do it all in one step?
Yeah, I did. 30, 29, 28. Oh, I see what I did. Never mind.
Okay. All right. Okay, next problem. A sample of 4 different calculators is randomly selected from a group containing 46 that are defective and 26 that have no defects. What is the probability that all 4 of the calculators selected are defective? So which rule are we using, or what are we looking for? Okay. Probability of 4 defective calculators. Okay, still multiplication. Okay. All 4 of the, right. Okay, so multiplication, because we're talking about defective and defective and defective. Are these dependent or independent? Dependent. Okay. So I'm not going to write out all the words this time. The probability that the first one is defective, 46 that are defective and 26 that have no defect. Altogether we've got how many? 72. So we're looking at 46 over 72. The probability the second one is defective, given that the first is defective. Right? And then we'll 44 over 70 times 43 over 69. Okay. So again, I'm going to multiply my numerators. And divide that by the product of my denominator. Okay, I got 0.1586 if I didn't make a typo. That's a choice, so we're going to go with it. Heck, it's about that. Okay, good. All right, so I mean, do you see that there's like you know, it makes sense to me. Of course, it makes sense to me. But I'm approaching it systematically. I'm thinking about the tools that we talked about in class because that's what it's about. It's not about these individual questions. It's about knowing when to use the multiplication rule, when to use the addition rule, when to think about complements, etc. Okay?
We've got the flow chart down pat, and we've got the rules figured out
Mm-hmm.
when to see them, and we can do okay on this. Is it safe to say that we'll do all right on this?
I will never say that, you know, because then you'll be like, well, you said,
Well,
you know,
I'm
but
saying, am I in the right track of feeling confident that I'll...
all right, I'm still going to say yes and no. You know, if you'd worked on this before we came here, then I would say yes. I'd probably feel comfortable. But, you know, right now we're working on it together.
Right.
So, you know, it would have been, you know, you still got a little help. You got to get to a point where you can do this without any assistance, except that mental flow chart that's in your head. Okay. All right, of 10 adults, at least one of them has high blood pressure. What's the question here? Provide a written description of the complement of the given event. So, what would the complement of this be? 9? Okay, so which choice is that? None. It'd be B, right? None of the adults have high blood pressure, right? At least one includes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
This is the at least one.
Well, we're getting there, it looks like. Okay? Right now it's just asking us about complements. So what is the complement? So kind of a little baby step right now. And so yes, none or 0 with high blood pressure, that would be the complement of at least one with high blood pressure. Okay? So how do we use that in problem 14? A study conducted at a certain college shows that 55% of the school's graduates find a job in their chosen field within a year after graduation. Find the probability that among 7 randomly selected graduates, at least one finds a job in his or her field within a year after graduating. So we're talking about the probability of at least one. So yes, that is one of my keywords. And the way that we handle that is by saying what?
Minus probability of none.
Okay, 1 minus the probability of 0. This was at least one with job. Okay, so we're going to have 0 with job. Okay. All right, so if we have 0 with the job, then that must mean there are what? Because we selected 7 people. 0 of them have a job, so that means what? 7 hungry people, that's right. Okay, 1 minus the probability of 7 with no job. Okay? And so that's where this brings us to the multiplication rule. We got to look at no job and no job and no job and no job. We got to do that 7 times. Okay? Keyword and. We're going to multiply. Are these events dependent or independent? Okay, independent. We're going to treat them as if they're independent. Okay, 55% probably came from a very large pool, and so, and we also we don't have a number, so we can subtract from top and bottom. That's right. So, all right, what's the probability then? Be careful about this, of no job for an individual. 45%. It was 55% that found a job, but we're interested here in those who didn't find a job. So that's the other 45%. And we're going to raise that to the 7th power, and that would give us our answer. Okay, questions about that? Okay. All right, number 15. A sample of 4 different calculators is randomly selected from a group containing 6 that are defective and 30 that have no defects. What is the probability that at least one of the calculators is defective? Okay, so again, an at least one type problem. Okay, so we get 1 minus the probability of what? 0 defective, right? It's 0 of the same type item, which means if I am selecting 4 calculators, then they must be 4 what kind of calculators? No, 0 are defective. Working, okay. Probability of 4 good calculators. Okay, and so again, that brings us to the multiplication rule. We're talking about good and good and good and good. Okay, are these events dependent or independent? Dependent. Okay, this is a relatively small sample size. If I take one out, of course, I'm not going to replace it, and that's going to change my sample space. So we're looking at the probability that the first one is good. So that's going to be what? 30 over 46, right? Because we had 16 that were defective and 30 that contain no defects. I took that one out. He's gone. What's the probability that the second one is good, given that the first one was good? Okay, 29 over 45, 28 over 44, and 27 over 43. Okay, that's what we would do to get the answer. Okay, questions about this?
Set that one on your calculator. You set that one up the same way that we were doing the numerator,
Mm-hmm. And I could even do the 1 minus in that one step. But this time I'm going to, since I've got that 1 there, I'm going to make sure I include my numerators in parentheses. And divide it by the denominators in parentheses. Did I miss something? Oh. Okay. Okay, so I get 0.832. Looks like it should be well, 3 decimal places, 0.832 works. Okay. Why do I write that? Because that's the complement rule. Remember, we said the probability of E plus the probability of E complement equals 1. And so to find the probability of the complement of an event, or the probability of an event, I should say, is 1 minus the probability of its complement. And so for us, that's what I did here. Probability of 0 is the complement of at least 1. And it's that's true. But the other reason why we do it is because otherwise I've got to calculate the probability of exactly 1 plus the probability of exactly 2 plus the probability of exactly 3 and 4, and it'd be easier for me just to look at the probability of 0 and subtract it from 1. It saves us some work and time. All right, so just that one event that's in the complement. All right, good. Okay, looks like I skipped a lot. What happened? Okay, we're right here? Okay. Whew. All right, the following table contains data from a study of 2 airlines which fly to small town USA. If one of the 87 flights is randomly selected, find the probability that the flight selected is an upstate airlines flight given that it was late. Okay, so we kind of talked about this a little bit earlier. What we're looking at here is called what? Well, that's the contingency table, but what they're asking us to find is what kind of probability. It does start with conditional. It's conditional probability. We're finding the probability that the flight selected is an upstate flight given. That's right. Okay? So if we're given that it's late, then we're ignoring those that are on time. All right? So now we've got altogether how many? 11, and we're interested in probability that it's an upstate airlines, so it's going to be 5 over 11. Okay? Well, good. Freaking out on the homework is good. As long as you, I know it probably didn't feel good, but as long as you're ready for the test, so that's okay. All right. All right, looks like we're almost moving into some counting. The library is to be given 3 books as a gift. The books will be selected from a list of 16 titles. If each book selected must have a different title, how many possible selections are there? Okay. All right, so the first thing I notice is how many. The second thing I noticed a couple of things. We've got 16 titles, right? And we're getting 3 books. So, what do you think we should do? Okay. All right, except with permutations, what do we have to have? Or what's the distinguishing feature of permutations? Not the exclamation point, no. Okay. All right, well, you're on the right track. We've got 16 books. 3 of them are being given as a gift. With permutations, the order matters. So, if we give them Little Red Riding Hood and the 3 Little Pigs and one more book, then we say, no, we're going to give them that other book and 3 Little Pigs and Little Red Riding Hood. Does that make a difference? No, the order doesn't matter. So in this case, it would be a combination. And so we would say 16 choose 3, which comes up to 560. Okay. Now somebody, you all might not be thinking this, but someone might think, well, why won't fundamental counting work? But generally, 2 things about fundamental counting that you need to consider. If you're drawing items from the same pool and you use the fundamental counting rule, then the order, what you're counting is orders. Okay? The other thing is, generally when we talk about fundamental counting rules, you have to be drawing items from separate pools. Basically, I said the same thing. But yeah, that's what makes the distinction there. So fundamental counting rule would not work here. All right, not work. And I guess in short, you could say if I think fundamental counting rule should give me an alternate answer, and you've got a problem like this where all the items are coming from the same pool. It's not like choosing so many Skittles, and then we're going to come over here and choose so many bags of chips. You know, those are different kinds of items. All of these things were books, and they were all coming from the same pool. No, that's not where I'm going with that. I just was thinking, I had to stop and ask myself, could I use fundamental counting? Maybe y'all didn't ask yourselves that, so we'll just ignore that for now. Okay? Here's another problem. 8 basketball players are to be selected to play in a special game. The players will be selected from a list of 27 players. If the players are randomly selected, what is the probability that the 8 tallest players will be selected? Just like that, you think? That's way too soon. But you could guess it. Yeah, but it has to be one of the rules. You got to use one of the rules. So which rule is that? Okay, so classical. So you're saying this is the total number of ways to select the 8 tallest. Okay, divided by the total number of ways to select 8. Okay, so only 27 ways to select 8. It's actually a little more than that, but we do need to think. Okay, probability of 8 tallest. I think the bottom number is usually easier to figure out. On the bottom, we're going to have the total number of ways that you could select any 8. It's big. It's what? Okay, and how'd you get that?
Same thing we did on the last problem.
27, choose 8. The order doesn't matter. Okay, I've got 27 objects, or people in this case, available. I'm choosing 8 of them at a time. Okay, 27, choose 8. All right, then up top, now, there's so many ways. I wouldn't even start to try to write them all out. But how many ways can you choose the 8 tallest? One way. There's only one way to choose the 8 tallest. If I choose 8 people and they make up the 8 tallest, there's no other way to choose the 8 tallest people. Okay, so it's 1 over the number that he mentioned, which comes from 27 combination 8. Okay? All right, I think we're getting near the end. I hope so.
Are we going to do a problem with, I'm not sure what it's called, not the choose, but it's the P instead?
Hopefully so. Let's see. This might be it right here. A pollster wants to minimize the effect the order of the questions has on a person's response to a survey. How many different surveys are required to cover all possible arrangements if there are 6 questions on the survey? Okay, because what happens here? What are we concerned with? The arrangements, the order. Sometimes the way that questions appear on the survey, this is kind of background information, has an effect on, we talked about that though in class, has an effect on the way that people respond. So there are 2 ways, considering the things that we talked about, that we could get an answer to this. They'll give us the same answer. Which rule? How many objects do you have available? 6. How many of them are we going to use? All of them. So which rule is that? That is the factorial rule. Factorial rule tells us how many ways we can arrange n objects. We're using all n of them. So we could say 6 factorial, which I think comes up to, well, factorial is a special case of the permutation rule. If you do on your calculator 6p6 is going to give you the same thing as 6 factorial. All right. So if you wanted to, you could ignore the factorial rule.
But the factorial rule is just the same as saying 6 times 7, 6 times 5 times 4 times 2 times 2.
Both of them give you the same answer. Okay.
I was freaking out. I thought I didn't have one of the rules, and I was like, no, wait, okay, I called it something different.
Yeah. Okay. You could do it permutation or factorial, and it comes up to, is that 720? Okay, 720 different ways. Okay. All right, let's see. Is this the last question? I think this is our SLO question. So I talked about this one already, but I'll mention it again here. Combination lock is open with the correct sequence of 3 numbers between 0 and 49 inclusive. If a number can be used more than once, what is the probability of guessing those 3 numbers and opening the lock with the first try? So the first thing I'm going to try to do is figure out what? How many different combinations, okay? And which rule do you think we'll use here? Combinations, okay? So if we use the combination rule, that means the order doesn't matter. Is that true when it comes to a lock?
Yeah, I think that we should probably use the permutation.
Permutations. The order in which we put the numbers in, that makes a difference. So our bottom number, because we are looking at probability, our bottom number is going to be, how many do we have to choose from? 50. Very good. Okay. 0 is the number. And then we're choosing 3 of them. How many of those result in opening the lock? Hopefully only 1. Okay, so figure out what 50p3 is. Don't do anything fancy trying to type that in the computer. Just punch it up in your calculator and say 1 over whatever that number is. Okay, which in this case is what? Okay, that's still not as many as I thought, but okay, good. All right, and I think that's a pretty good representation of what we've talked about. So any questions about any of that? Any questions about anything else? I think it's all very systematic. You know, if you know those tools, then you'll be able to approach the problems correctly.